This is content of part 1a and 1b. If you're interested only in a specific part of this video, just jump to its start time. In a nanomagnet, the PMA effect is induced by spin-orbit interaction. The spin-orbit interaction is a very rich effect. I am planning to make a separate video about it. Also, you can find the detailed explanation on my website, which is here. Since the spin-orbit interaction is very important for this measurement, I will explain very shortly about this effect. The name spin and orbit is historical, a little confusing, and does not represent the true nature of the effect. In fact, the effect is relativistic. The effect of spin-orbit interaction describes the fact that electrons which move in an electrical field experience a magnetic field as well. This is due to the relativistic nature of electromagnetic field. For the same reason, an electron experiences an electrical field when it's moving magnetic field. Such force is called the Lorentz force, and the effect is called the Hall effect. Therefore, the first fact about the effect of spin-orbit interaction is that the effect describes the magnetic field. It's absolutely real magnetic field, as real as any other magnetic field of different origins. As any relativistic effect, the spin-orbit interaction is a small effect. It can be large only in large electrical field. In a solid, such electrical field exists only in close proximity of a nucleus. This is my second fact about spin-orbit interaction. In close proximity of nucleus, the electron orbital is center-symmetrical. If you look closer, the orbital can be divided in two equal passes where the electron moves in clockwise and counterclockwise directions. For these two passes, the electron experiences an equal but opposite magnetic field of spin-orbit interaction. As a result, the two contributions compensate for each other, and in total the electron experiences no spin-orbital field. When external magnetic field is applied to orbital, the electron experiences the Lorentz force, in red, which is opposite for clockwise and counterclockwise moving electrons. The additional Lorentz force changes the orbital radius. One path becomes closer to nucleus and another path becomes farther from nucleus. As a result, for each path, the electron experiences a different electrical field of nucleus and therefore a different magnetic field of spin-orbit interaction, shown in green. There is no more full compensation, and in total the electron experiences a non-zero magnetic field of spin-orbit interaction. It means the magnetic field of spin-orbit interaction follows exactly the external magnetic field. As magnitude or direction of the external magnetic field changes, magnetic field of spin-orbit interaction changes correspondingly and proportionally. Fact number 3 is that magnetic field of spin-orbit interaction is linearly proportional to external magnetic field. The proportionality coefficient is called the coefficient of the spin-orbit interaction. In the following video, I will show you how to measure it, how to control it, and how to engineer it. It might be some nonlinear contribution here, but it is only substantial and therefore important at a rather high magnetic field or for some specific cases. As you will see later from my experimental measurement, considering only the largest linear contribution is sufficient for many cases. Also, please note that in the case of non-symmetric orbital, for example of the p or d symmetry, the story is slightly different, but the conclusion is the same. The magnetic field of spin-orbit interaction is linearly proportional to the external magnetic field. And another fact, which I will not explain today in details, is that the spin-orbit interaction cannot break the time inversal symmetry by itself. The spin-orbit interaction can manifest itself only when the time inverse symmetry is already broken. That fact leads again to the same linear proportionality between external and SO magnetic fields. And the final and very important properties of spin-orbit interaction is that the strength of the spin-orbit interaction depends on the orbital deformation. And additionally, the SO strength depends on direction of magnetic field with respect to that deformation. A centrosymmetric orbital whose center coincides with the nuclear position has a weakest spin-orbit effect. There are two main types of deformation which lead to enhancement of the spin-orbit interaction. The deformation which influences the spin-orbit interaction the most is the shift of the position of orbital center from a nuclear position. Such a shift creates not only a large magnetic field of spin-orbit interaction, but also a large electrical dipole. The second type of deformation is a squeezing of the orbital along one of the axes. The more the orbital becomes elliptical, the stronger the spin-orbit interactions becomes. For the orbital of elliptical symmetry, the strength of spin-orbit interaction depends on the direction of the external magnetic field. The strength is different for the direction along and perpendicular to the deformation. As a result, the magnetic field of spin-orbit interaction is proportional to external magnetic field for both directions of the magnetic field. However, the proportionality coefficient KSO depends significantly on the direction of magnetic field with respect to the orbital deformation. It is smaller when the magnetic field is applied perpendicularly to the deformation, and it is larger when the magnetic field is applied along the deformation. I would like to emphasize once more a very important properties of the spin-orbit interaction, and that the magnitude of magnetic field of spin-orbit interaction depends on direction of externally applied magnetic field. You can understand the reason why the spin-orbit interaction depends on the shape of the electron orbital from these two animations of circle and elliptical orbitals. In the case of circle orbital, the electron is equally distant from the nucleus and therefore experience equal but small electrical field, which results in rather small magnetic field of spin-orbit interaction. In contrast, in the case of elliptical orbital, the electron experiences very large electrical field and, as a result, large HCO when the electron is in very close proximity to the nucleus here. Even so, there is only a part of orbital when the HCO is large, and for the remaining parts the HCO is negligibly small. On average, the HCO is substantially larger for the elliptical orbital than for the circular orbital. Even so, these two pictures of orbitals are very simplified. They explain the general tendency. The more the deformed and asymmetric the electrical orbital is with respect to the nucleus, the stronger the spin-orbit interactions becomes. This is experimental proof of this just explained important fact that the strength of the spin-orbit interaction depends on the direction of external applied magnetic field. The graph shows some measured value, which is proportional to coefficient of spin-orbit interaction in iron-boron nanomagnet as function of external magnetic field. This axis, Hx, is the in-plane component of the field. This axis, Sz, is a perpendicular to plane component of the field. As you can see, coefficient of spin-orbit interaction has a maximum at specific angle of applied magnetic field. The shape of peak values are lines, not a radius, not a dot, but lines, which means the angle. The dependence of coefficient of spin-orbit interaction on the angle of the applied magnetic field is one very expected property of the spin-orbit interaction. And this is a clear experimental proof of this important property. I will explain in more detail about this measurement and what it is actually measured in this experiment in the following parts of this video series. The origin of the PMA effect is the spin-orbit interaction, and as explained earlier, the spin-orbit interaction is substantial only for deformed anisotropic orbitals. In the case of an isotropic material like amorphous iron or cobalt, there is no PMA in the bulk of material because in the bulk their orbitals are symmetrical. All orbitals on the top interface layer are deformed and therefore experience a strong spin orbit and PMA. The uniqueness of the PMA effect is its strength. The PMA is so strong that even if it exists only in one top layer, it determines the magnetic properties of whole bulk of the nanomagnet. Since the bulk orbitals force the magnetization to align in the plane direction, and interface orbital forces to align perpendicular to plane, the magnetization of nanomagnet depends on the film thickness. The equilibrium magnetization is in plane in the case of a thicker film because there are more bulk atoms. And in the case of thinner film, the magnetization is perpendicular to plane because there are less bulk atoms. Because of its strength, the PMA effect is very important for nano-sized devices. It's critically important for high-density hard disk, magnetic memory, and nano-sized sensors like this. If you are interested to see the content and other parts of this video, you can find the links below this video.